Okay, this is a video for more of the applied problems from section 2.2. We're going to start with example number 2. We did example 1 in class. This one is dealing with money and taxes. So let's read the problem, see if we can set up our list of variables and then set up our equation and solve. It says a couple does not wish to spend more than $70 for dinner at a restaurant. So that's their budget, that's their max. If sales tax of 6% is added to the bill, and then they plan to tip 15% after tax, now that is weird, but that is what they've decided to do, what would be the most they could spend on the meal? So we have to think through this in stages because there's the meal that we don't know what they've bought, then there's the after-tax price of that meal, and then there's going to be the tip on top of that. So let's start with letting X equal the amount spent on the meal. Now, if you were doing tax, remember you multiply that by 0.06 and then you add it to the original amount. The original amount is X plus 6% of X, so 0.06 times that, which means that if you add those together, that's a 1 and a 0.06, that would be 1.06X. That would equal the meal plus the tax. Okay. Now, this will be our final step because I'm kind of working this in stages because I want to get to the final stage all at one time. The 15% is 0.15 times the 1.06x. So notice that part right there is combined. This is actually saying, okay, how much are they going to spend in tip based on what they've already spent on tax and meal. So we're going to use our calculator to work that part out. So this is 1.06 times 0.15 is 0.159x. So let me double check that, make sure, yes, I did type those in correctly. This is just going to be the tip amount. Okay, so if you think about it, there's three main pieces here that are going to get added together. The money spent on the meal, the money they spent on the tax, and the tip amount. If you want to simplify your life, you can use the 1.06 because it actually stands for meal plus tax, or you can keep these three things separate. So if you wanted to do it separate, it would be meal plus tax plus tip needs to be no more than $70. So we know that $70 is our max, but if honestly you wanted to make this realistic based on what they've said, because they said no more than, then we really need to say less than or equal to. So x plus 0.06x plus 0.159x less than or equal to 70. We add together our pieces. We already know it's 1.06 for meal and tax plus the 0.159. That's 1.219x less than or equal to 70, and we will divide 70 by that decimal, which is 5742. So they need to spend less than or equal to $57.42. Now, the reason it's okay to say equal to is because this actually is bigger than 42 cents. It goes up past that in decimal points. So if we round down there to that hundredths place, then just keeping it at a 2 is actually okay. You do have to be careful about the rounding when you say eat less than or equal to or greater than or equal to. So that would be as much as they can spend on their meal. For example number 3, we have a workman whose basic hourly wage is $10, but he receives 1.5 times his hourly rate for any hours he works over 40 a week. If his paycheck for the week is $5.95, how many hours of overtime did he work? Well, there's a couple different ways you could approach this one, but let's let X equal the number of hours overtime And what we already know is that he worked 40 hours, because if he didn't work 40 hours, he wouldn't be getting overtime. So the first thing I would think of is that the 40 is getting paid at $10. And I know that we want this to equal his paycheck for the week, so that's the $5.95. What's going to matter here is what's going on in the middle, and his overtime, remember, is time and a half. So it's 1.5 times his normal rate of 10, which is $15 per overtime hour. So we know that his X that we're looking for is being times by $15. So this is 400 plus 15x equals 595. We subtract over the 400, and we're dividing 195 by 15, which is 13. So he worked 13 hours of overtime to make the check that he did. Number 4, a consulting engineer's time is billed at $60 per hour. Her assistant is billed at $20 per hour. A customer receives a bill for $580 for a certain job. What we know about this group is that the assistant worked 5 hours less than the engineer. So how much time did each person get on the job? Okay, so we know that X is going to be the engineer. I always let the person that they are relating to, so notice it says assistant is blah, 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 than the engineer. This is who I usually let be X, because if I know that that's X, the assistant should be smaller than that in hours, so X minus 5 will be the assistant's hours. Okay, so then we can put this together. $60 for every hour the engineer works, so 60X plus, because the assistant's also on the bill, $20 for every hour that the assistant works, which is the X minus 5, and the customer was billed for a total hourly rate bill of $580. So we distribute the 20. We add our like terms over here, and we can add our 100 over, and we would divide the 680 divided by the 80. And that looks like it's 8.5. Now that's the hours for the engineer. That means that 8.5 minus 5 will be the assistant's hours. So that would be 3.5 hours for the assistant. And we have now found both pieces of information. Now I know I did this one in class, but I'm going to do it again because one of my groups didn't get to see it. So a pharmacist is to prepare 15 milliliters of special eye drops for a glaucoma patient. The eye drop solution must have a 2% active ingredient, but the pharmacist only has 10% solution and 1% solution in stock. How much of each should be used to fill the prescription? So we have these two buckets of two different types of medicine and their different concentrations that somehow we're going to mix a little bit from each to make a 15 milliliter solution at 2%. I always put my percent label down here and the amount of liquid in the box, the actual beaker. So the question is how much is in each of these. So one of these is my 10% solution and the other one is a 1% solution. I already know that I should have more of the 1% because you only want this to end up being 2%. You can't add too much of the 10%. And usually you just let one of these be X. The trick is a lot of people learned how to set this up using Y for the other bucket. But the problem with that is that means you have to have a system. You'd have to have two different equations. I'd like to avoid having two equations, so if this was a 5, you'd tell me that there's 10 in this bucket because this has to add up to 15. So the second bucket is 15, the total amount for this, minus however much we already used in bucket 1. And then all we need to do to set this up is multiply each percent times its bucket amount and then solve for X. Now, you could change all these to decimals. That's not necessary since every single term has a percent. So 10 times X plus 1 times 15 minus X equals 2 times 15. That's 10X plus 15 minus X equals 30. 9x if I combine my like terms, and that would equal 30. And then I get 9x equals 15 if I subtract the 15 over to the right side and divide by 9. So we'll need to get our calculator, because if you're in a word problem, it is okay to go to decimals. So that's 1.7 if we round to the nearest tenth. They didn't specify. So about 1.7 milliliters, and you need to tell me of which one, of the 10%, because that's the x. To find the other one, you do 15 minus that answer. So 15 minus 1.7 would be 13.3 milliliters of the 1%, which makes sense because you need a whole bunch of 1% and just a tiny bit of the higher concentration to bump the whole thing up to 2%. Now this is another one very similar to that. This is about an asthma medicine that is to be prepared from an elixir with a drug concentration of 5 milligrams per milliliter and a cherry-flavored syrup that is to be added to hide the taste of the drug. So this time you're not mixing two of the drugs together, you're mixing a drug concentration with something that is not got any drug. That means it's 0% drug. And then we want to know how much of each must be used to prepare 100 milliliters with a 2 milligram per milliliter concentration. So we think of our buckets again. Final result should be 100 milliliters at a concentration, not really of a percent, but of milligrams per milliliters. We have this is the original drug. This is the cherry syrup. Cherry syrup has no active drug in it. So that's 0 milligrams per milliliters. The drug that's active is 5 milligrams per milliliter. And again, we can kind of go with the same philosophy. Let this be x. The other one would be 100 minus x. The nice thing about this scenario is you're going to multiply by 0, which means this whole middle bucket's going to go away. So it ends up just being 5x equals 2 times 100. So 5x equals 200. If you divide by that, you get that x equals 40 milliliters of the drug, which means you actually need a bunch of syrup to hide the nasty flavor of this. So you need 100 minus 40, you need 60 milliliters of the syrup. So quite a bit of the sugariness to hide the nasty taste. Okay, I'm going to go through the rest of these just so that we have a better place to start off next time in class. I will also be recording a video of just the beginning of 2.3 because it is just a review of factoring again, of how to solve equations with factoring. So both this video and that one will be posted, of course. Example 7, it has to do with distance. It says a runner starts at the beginning of a runner's path and runs at a constant rate of 6 miles per hour. 5 minutes later, a second runner begins at the same point running at a rate of 8 miles per hour, following the same exact course. How long will it take the second runner to reach the first? Distance is, remember, d equals r times t. There's two ways a distance formula can be set up, and it depends on which type of situation they give you. d1 equals d2 means they went on the same route, or they've caught up to each other, essentially, on the same route. d1 plus d2 equals total distance usually means that people are running opposite ways, maybe towards each other or away from each other. Okay, so in this situation you weren't given any total distance, but you were told that they were following the same course, so that means we're looking at this scenario. So what I usually do to help me with these is I set up a little chart called the D equals RT chart, and I label what my two distances are. Distance 1 is going to be runner 1, and distance 2 is going to be for runner 2. We know the rate of the first runner was 6 miles per hour. We don't know their time yet, so we'll talk about that in a minute. We know the rate of the second runner was 8 miles per hour, so a little bit faster, but this person had a late start to the actual event. So this person, runner 2, started later. Now, one of these people has to be X, the other one's going to have X and something to do with the 5 minutes. The best way to set this up is to let the person who ran the longest time to get the 5. The runner 1 ran 5 minutes longer than the other runner because he had a head start, because this person was actually stalled for 5 minutes. So I'm going to let runner 1 be X plus 5. That says that they ran the same amount of time as runner 2 plus an extra 5 minutes. And I'm going to let runner 2 just be X. So those are my two unknown times. This person ran until they caught up with that person. This one ran that same amount of time, but an extra 5 minutes at the beginning. Now, because this is D1 equals D2, you just need to multiply the R and the T together and set them equal for both people. So D1 equals D2. We distribute. I would subtract my 6X over, divide by 2, and it looks like it takes 15 minutes for runner 2 to catch runner 1. Okay, so that's a distance problem. So that's another type of problem you can encounter. The next type is something called a work rate problem. These are always somebody works a job at some rate, someone else works a job at a different rate. What would happen if they worked together? The problem with that is that you have unequal time measurements because someone worked for 5 hours and the other person worked for 8 hours. The only way you can compare them and actually add them together is to say, what did they do in 1 hour of work or 1 minute of work or whatever it is they're measuring time in. So for this one it says, because usually we have what is called a fraction rate or unit rate for number 1, whoever that is, plus a unit rate for number 2 equals a combo rate. That's kind of the situation. Now, the only time this changes is if the two people are doing opposing jobs, like one is cleaning up and one is messing up, or one is painting a room and one is, whitewashing it again, or one is filling a tub and not filling a tub, or draining it. So if they're doing opposite jobs, the only difference is this becomes a minus. So the situation we have to figure out is what are we going to measure our time in? So with water from one hose, a swimming pool can be filled in 8 hours. So hose 1 takes 8 hours to fill the pool. Hose 2 by itself takes 5 hours to fill the pool. So notice they're doing the same job. How long would it take if they work together, which I call the combo? Okay? Again, because they're measuring in different times, that's hard to compare. We consider these one of those things where we don't actually do the real world here, because in the real world someone's going to stop and take breaks. They're not going to paint for 8 hours straight or fill up a pool for 8 hours straight. But to make this math easier, we consider that this person or thing worked at a consistent rate the whole time. So if you consider it that way, that means that this person filled up 1/8 of the pool, this hose did, per hour. Because you would have, think about 8 blanks, and each one of those is 1/8, 1/8, 1/8, 1/8, 1/8. If you added them all together, it'd be 8/8, which would be one job completed. This one is doing it in 1/5 of the pool per hour. And then because we don't know this one, we're going to call it 1/x. They all need to have the same format. So then we write this as 1/8 plus 1/5 equals 1/x. I would use an LCD of 40x to clear out my fractions. So I'm just going to write that right here, that I'm going to multiply each fraction by 40x. We have some canceling that'll happen. 8 goes into 40 5 times, so this would leave me with 5x. Kind of highlight that and separate those. 5 goes into 40 8 times, and there's an x still, so 8x. And x cancels with x, so this is equal to 40. That is 13x equals 40. We want to divide, and again, because it's a word problem, it's okay to go to decimals. So this is 3.1. So it would take them approximately 3.1 hours to fill this pool if the two hoses worked at the same time together. Okay, I'm going to come back to number 9 because it's different, but 10 is just like that one. So this one says it's in minutes this time. So it takes Sarah 45 minutes to deliver newspapers on her route by herself. So that means she does 1 out of 45 newspapers per hour. Her brother, which we don't have a name for him, we don't know how much it takes him by himself, but we do know because it says if he helps, it takes 20 minutes. So that means the combo is 1 out of 20. So that means the brother is the 1 out of X. It's okay for you not to know either the combo or one of the singles. So when we write this out, it's always the two individuals separated out with a plus equal to the combo rate. So we have to think, what does 45 and 20 both go into? 45 times 2 is 90, times 3 is 135, times 4 is 180, and 20 will also go into 180. So I'm going to multiply this whole thing by 180x. That will be my LCD. So let's write that out. 180x times 1 over 45 plus 180x times 1 over x equals 180x times 1 over 20. That was 4 times, so that would be 4x. This will be plus 180. 20 goes into 180 9 times, so that would be 9x. We would subtract over the 4x, that would be 5x. And 180 divided by 5 should go evenly. We get 36 minutes, because this was in minutes, not hours. So the brother by himself can do the job of the newspaper route in 36 minutes. So he's actually more efficient than his sister. All right, I only had one more example from this. I'm going to go back up to number 9. This is more of a common sense money problem. Many of you have gone to a store before and you've needed to buy something on a sale. So Donnie bought a shirt that is 35% off and he paid $17.55. So this is the sales price. It's not the original price. What was the price of the shirt before the discount? If you remember how a discount works, you usually have an original price minus a discount, and that equals your sales. What's difficult is that the student's always confused what the discount is. The discount is always a percent of the original price, so it has to have two components, a percentage times whatever original price is. Well, we don't know the original price, so we're going to let X be that. So this is X minus, the percentage off is 0.35. It does need to be a decimal since not everything has a percent, times the original price again, which is X, equals $17.55. Think of that being a 1. 1 minus 0.35 is 0.65X. And just to double check yourself, add those back together, it should make a 1. And then this is 0.65 that we're going to divide by. So 17.55 divided by 0.65. And it looks like the shirt originally cost $27 before the discount. Okay, that is the end of 2.2.